Hello and welcome. We are now going to solve problems on the topic section 2.1. If you have not watched the video on the same topic, please watch the video in the playlist. That should be the video right before this. And this should be the protocol for every future lessons also. First, watch the video and take notes on your note taking guide of the lecture, and then come to the um, part where we solve the problems. And here also keep the problems ready, download the file, keep it ready with you, and fill it out with me. Okay. The first problem: a cardiac monitor is used to measure the heart rate of a patient after surgery. It compiles the number of heartbeats after T minutes. Okay, so there is a table here which has the time in the first row and the number of heartbeats in the second row. When the data in the table is graphed, the slope of the tangent line represents the heart rate in beats per minute. Okay, because the time is in minutes here, and then the second row is the number of heartbeats. So if you take the slope y2 minus y1, x2 minus x1, gives you the heart rate. The monitor estimates the value by calculating the slope of the secant line. Use the data to estimate the patient's heart rate after 42 minutes using the secant line between 38 and 42. Okay, so this is a very simple and specific question. It tells you what exactly to do. You need to uh, estimate the heart rate after 42 minutes, and for that you are going to use a secant line. And what secant line? With the points at 38 and 42. So you can imagine, okay, let's say, no, I don't know how the heart rate is, the graph is, I'm just going to make an assumption. Let's say if the heart rate was some graph like this, then you are looking at 38 and 42, on the time scale, which is going to be the x-axis. This is a, like, you don't need to do this to um, solve the problem. H for heart rate, T for time. Okay. But this clarity helps you in the future also. Okay. Then you might be remembering, this is what exactly we were studying earlier in the lecture slides, right? So we are finding the slope of the secant, which would be the slope of the tangent at that point. Okay. So the tangent here, that would be the actual heart rate of the patient at 42 minutes. And this the one that we are calculating here is a secant which is close to it. Okay, approximation, right? And let's do that. Answer is very simple. Okay, now the answer part is simple. Okay, the slope of the secant, mpq, in the notation, according to our lecture, is y2 minus y1. I'm going to write the formula here for the sake of completion. Okay, over x2 minus x1, and that will be 42 minus 38 over 3020 minus 2720, and you punch that in a calculator. Okay. Okay, so when you calculate that, you get 75 beats per minute. Okay, and that's your answer. Okay, next, the displacement in feet of a certain particle is given by that formula, s equals t cube over 8 on a straight line. Okay, find the average velocity on the interval from 1 to 1.15. Again, similar to the tangent problem, right? The average velocity is the slope, 1.15, will be the distance at 1.15 minus the distance at 1 divided by the time gap. 1.15 minus 1 or 0.15, if you can think about it and write it directly. Okay. And that's going to be 1.15 cube divided by 8 minus 1 cube divided by 8 whole divided by 0.15. Be sure to punch this in a calculator correctly, and I will be showing you that in the video as well. Okay. Now, in any calculator that you use, the fundamental, the notations would be the same. Okay, although your keys, if you in your Texas Instruments calculator will be different. And when I'm showing you the work here, I'm not going to be simplifying that expression. Although you can do that if you are able to do it, and then your typing on the calculator itself will be easier. But I'm going by the assumption that we will not do any simplification before we do the calculation. Okay. So I have to divide two things here. So what I'm going to do is this. I'm going to use parentheses first because I know the numerator is going to be a complicated expression. It's 1.15 cubed, right? So to the power 3. Okay. And then it's divided by 8 minus, and now I didn't have to put parentheses because the precedence, right? The division takes place before multiplication. So this is already taken care. Close the bracket. Okay. Close the parenthesis. That's the numerator part. 1 cube is 1, so I skipped that part. That whole thing is divided by 0.15. Okay. 0.434 is what we get. Let's see. Do we have 0.434? Yes, we have 0.434. That is your 0.43. 0.434. We will actually also write the unit. Okay. Feet per second. All right. If a ball is thrown into the air with a velocity 60 feet per second, the height is given by that. I was talking about the laws of motion, in the lecture video. So if there is some initial velocity, that also appears in your equation of motion. Okay, here it is 60t. The initial velocity is 60. And from there you subtract minus 90 square because the acceleration due to gravity is going to pull it down, so the velocity will decrease over a period of time. And question is find the velocity when t is equal to 9. Okay. So how will you do this now? At this stage, at our current stage, the way we do this is by approximation. Okay. So what you have to do is at t equal to 9, you have to look at a small, like, interval. Okay. So like right now, I suggest the approach. You calculate the average velocity on the interval 9 to 9.1, and that will give you an approximation. Okay. And then maybe after that I will discuss a more precise way of calculating it. 9 to 9.1. Okay. And at that time it will be h, the height reached at 9.1 minus the height reached at 9 divided by the difference in time, 0.1. Right. That will be the average velocity on that interval. And according to formula, that will be 60 times 9.1 minus 9 times 9.1 squared minus 60 times 9 minus 9 times 9 squared whole thing divided by 0.1. Now, do that on a calculator. This time I'll skip showing it to you, the whole process. I'll just show you the final screen. Okay, so I had forgotten to put the main outer set of parentheses. Sometimes it happens, right? So what I calculated here is the numerator part. Okay, and once I calculate this, the denominator is divided by 0.1, which is basically multiplying by 10. Okay, so let us calculate this. That is minus 10.29. So it will be minus 102.9. Okay, so this value will be negative 102.9. And the speed, it will be feet per second. Okay. And where do you get that? 102.9. So it's closer to 102. See, sometimes it's so close. Okay, 104 is also there, but 102 is more closer. So the nearest answer is that. Okay. Um, just a quick note here. What's the negative? You might wonder. We're talking about velocity. Why do we have a negative value? That means the ball is now falling down. Actually, yeah. If it is going up, then that's positive velocity. You know and when it is coming down now, it will be negative velocity. So by this time it is already back on its way to the ground. Okay. Oh, by the way, sorry. 100, like, how do you know? Sometimes you might have a confusion. Okay, just to elaborate a little bit more on this, we got 102.9 because we are taking an average velocity, right? So if you are not sure, you might want to, like, if there was another option which was really close, like 102.5, let's say, it would have been a little tricky to decide, right? So what you should do is you should calculate the average velocity on 9.01, or, like, let's say 0.5 for me, make the interval smaller and then see where to which number it gets more closer to. That would be ultimately the instantaneous velocity. Okay, that's the thinking process. Um, I was saying earlier that I will also give you another method. This will be like in a precursor to, like, the techniques that we'll be studying later. Okay, so you are already seeing enough of it, so why not, let us do it. A formal way to do this would be, a precise way to calculate the instantaneous velocity would be, you calculate the average velocity on 9 to some 9 plus h. Okay, where h is a arbitrary number for now. And according to formula, that is 60 times 9 plus h minus 9 times 9 plus h square minus, right, 60 times 9 minus 9 times 9 squared divided by, now from 9 to 9 plus h, the difference is h. Okay, let us compute that. You might remember from college algebra or pre-calculus, this is the quantity called difference quotient. You see, you study everything for a reason. Okay, at that time when you are introduced to difference quotient as a function, you might have wondered, why do we do this? Here is an application. Okay, that's the difference quotient, and let us simplify it. Okay, so I will skip some basic algebra part for now. You will understand. Okay, this 60 times 9, 69 times 9 cancels, so you will get 60h from the, when you distribute that, 60h from the first term, minus, here, this 9 plus h whole squared is a plus b whole squared formula. Okay, 9 square plus 2 times 9 times h plus h squared. Okay, in that, you now observe this 9 square, 9 will multiply with that 9 and cancel here. Okay, 9 times 9 square will cancel. The other two terms will survive, right? So what will survive? They are both negative sign. Negative, this is 18h. Okay, so 9 times 18h and negative 9 times h squared. Those two terms will survive, divided by h. Now, what you observe is every term in the numerator has an h in it, right? So you factor that h out. What do you get? You could have simplified that first, maybe actually. So 9 times 18 is there. That is calculation is going to be 162. Okay, so 9 times 18 is 162. So 60 minus 162, negative 102. That is the first two terms minus 9h. Okay, when you factored that h out, what remains in the parenthesis inside the bracket is that divided by h. Now you see what's going on here. This h could be cancelled with that h, right? As long as you know you have some finite interval where h is not 0. So this is negative 102 minus 9h. Now you see why the answer is negative 102. Okay, what is happening? When you take smaller and smaller interval, this goes to 0 as h goes to 0. That's the language of limits we will be formally discussing very soon. Okay, this will be the average velocity, but when you take small interval, that h is very small. So that part, that second part, minus 9h is going to be almost 0. Hence, your instantaneous velocity will be negative 100. That's the process. Okay. A good introduction to the way we will calculate limits or derivatives and limits later formally. Okay, here's another question. The position of a car is given by the values on the table at different times. Find the average velocity for the time period beginning t equals to 2 and lasting 2 seconds. Now is the time I'll be skipping actual solutions because we have already done this. Okay. Beginning at t equal to 2 and lasting 2 seconds. So that is from 2 to 4, right? So we're talking about average velocity on the interval 2 to 4. And follow the procedure from before and calculate it. That is your work. Okay. Suppose the distance covered by a moving car on a straight line is given by that formula. Can calculate the instantaneous velocity at t equal to 34. This is like the ball that was thrown up and was falling down. Same technique, you can do it. Rock is thrown upwards and there is that average velocity on that interval. You can again like simply calculate it. I'll just simply repeat the formula here for you, and there is a way of writing, so I want to just do that here. Okay, the rest you can do. You can write like this is y of 3 minus y of 2 divided by 3 minus 2. Okay, average velocity on that interval. What I wanted to like talk here, sorry, is this notation. Okay, y of 3 minus y of 2, that's not multiplying, it's not y times 3. Okay, y of 3, now the y as a function of t. I know like you are students in calculus, you are quite familiar with these terminologies, but sometimes we tend to miss the minor points at lower level classes and get confused here. So I want to make sure you are not confused. We write y equals f of x as a function, and then if I have to evaluate the value of y for a particular x, like y equals f of 3, that would be the value of the function at 3. That we easily understand. Okay, but you have to understand here f is simply a dummy new symbol for y. Okay, so many times you will see in textbooks you can simply say y equals y of x. When you understand, when the context is clear, y is a function of x. That's what we are saying, right? So some authors will go, why to introduce another letter? Just say y of x. Y is a function of x. So in that sense, this is y of 3 minus y of 2 divided by 3 minus 2. Okay. The rest you can do. Okay. A point P164 lies on the curve if q is the point x comma root x. That's the equation of the function, right? Y equals root x. That's the curve. So any point on the curve will be x comma y. That y is root x. Use your calculator to find the slope of the secant for the value 3.59. Okay, where p is fixed. P is that 16.4 and you are taking a neighboring point at 3.59. So this is now using the secant, the tangent problem where you find the slope of the secant. Okay, so MTQ is what? Um, I mean root x minus 4, right? For any x, and that is y2 minus y1, and x2 minus x1 would be x minus 4, sorry, x minus 16. X is the x coordinate is 16, y coordinate is 4. So root x minus 4 q minus p, okay, divided by x minus 16. And then what you do, you plug in 3.59 for x. Okay, all right. Root 3.59. 1 second, I want to make sure I'm doing the. Oh, no, no, no. Did I say something wrong here? Give me 1 second. Okay. Y2 minus y1. Okay, I think I wrote the y2 minus y1. And root 16 minus 4 root x minus 4 over x2 minus x1 and secant pq where x is 3.59. Y equals root x. Okay, yeah. Sorry, we did it correctly. I was just second guessing myself because of the way the values are given. Okay, these are weird choice of values, I would say, because 16 is 4 square, right? So I was just for a second thinking if we mixed up, x with y, but looks like we did not. Um, do that calculation. Now I want to make sure that I'm also doing the correct thing. I will pause the video and use a calculator to check that. Um, that is how I typed it. I just wanted to show you that in my this screen calculator here, when you put that under root sign, it already automatically opens that parenthesis. Okay, so I had to be careful. I had to close the parenthesis before I subtracted 4. Otherwise, it would be under root of 3.59 minus 4, whole thing under the root. That's not correct. Some small things you have to be careful sometimes. Okay. Um, the rest of it is usual. Make note of the parentheses. Let's see if we are on the right track. 0.1696 is anything close to it. 0.1696. Okay. Thank God. All right. A tank, 100 gallons of water, which drains from the bottom of the tank in half an hour. Okay. 100 gallons in half an hour. 1000, sorry. 1000 gallons in half an hour. The values in the table show the volume of the remaining. Okay. volume remaining after certain number of minutes. See the interesting thing here, okay? It empties, from the bottom of the tank. This is an opportunity to talk physics, right? Which is very much mathematics and calculus. Now, when water empties from the bottom of the tank, you might think, if it takes like half an hour for 1,000 gallons, you could simply calculate like, in 10 minutes, in 5 minutes, just by dividing, um, proportionally. Thing is, that's not how it works. Why? Because of pressure, right? Initially, when the tank is full, the water is going to gush out, at speed because of so much pressure. But as the pressure decreases, the rate at which it will go out will be less. Okay. So it's not going to be a straight line, a curve. It's going to be some parabolic thing, I guess, if it is quadratic. Okay. Off top of my head, I don't remember. Or hyperbolic because it's some inverse relation. But these are the table of values, and you will not find that proportionality. Not a linear thing here. Okay. Let's see. Let's continue. The values in the table show the volume after a certain time. P is the point 15,290. So that means after 15 minutes, 290 gallons is remaining, right? Fill the table with slopes of the secant. PQ, where Q is the point on the graph corresponding to time t. Okay. Why did they say 15,290 and in the table there is a different value? I don't know. I'm just assuming that this is a typo. Okay, either the 290 there or on the table, one of them is a typo. Let's go with this correction. Okay, make that 290 and let's calculate. So the first one I'll show and then the rest you can continue. The answers are given here at the bottom. You can check, but please do on your calculator and check. Okay. So when t is 5, what are we talking about here? P is 15 comma 290, right? So like the expansion here would be PQ. So I want to make sure that we take this as Q. This would be our point Q. So Y2 minus Y1 would be 686 minus 290 divided by 15 minus 5. Okay, that will actually immediately tell us what value we should have here. It makes sense that this is 396, yes, divided by 10. So 39.6, that's correct here. Oh, one important thing here. 5 minus 15, right? Sorry. We have to maintain the order. Okay. Q. For this should be I should take the X and Y from the Q first and subtract the X and Y from the P. So that's negative 10 there. That's negative 39.6, which is what is given here. Okay. That will be the first thing here. And then you can continue. Okay. A position of the car is given by this. Estimate the instantaneous velocity by looking at these further periods. Okay, so you do it. Okay, it's not a difficult problem. Calculations you can do. I will only talk about the idea. We want to get the instantaneous velocity at 2. Here we are introduced or reinforced the idea that you don't always look from 2 and later, right? We talked about that in the lecture also. You can look on the interval ending at 2 or starting at 2. The thing is, you try to make that interval smaller and smaller ultimately, right? So you first take the interval 1 to 2 and then 2 to 3 before and after. The meeting point is 2, which is where you are looking for the instantaneous velocity. And in order to for your estimate to be correct, you would expect them to be more or less similar. See, the point is that these two average velocities, V averages, okay, should be, I'm writing that literally here, we should be similar. Only then you can be confident about your estimate. For example, if the answer is 26.5, you should be getting average velocities, I don't know, 25 or 27 or close to that on both sides. On one side you get 25 feet per second and the other side give you 50 feet per second. You cannot say your average is 26 point. Okay, that will be not good intervals then. Many times that can happen, by the way. Just because that happens, you don't say that the limit does not exist or the instantaneous velocity cannot be found. You cannot say that. You have to reduce the interval in those cases. Okay, instead of taking 1 to 2, you take 1.5 to 2 and 2 to 2.5. Make it narrower and narrower, and even then the values on two sides are going to be different. Then you say that there is no limit or the instantaneous velocity cannot be determined this way. Okay. All right. The point 0.51 lies on the curve y equals sine pi x. Quick review of your trigonometry there, right? When x is 1, um, you get, sorry, when x is 0.5, you get sine pi over 2. Pi times 0.5 and sine pi over 2 is 1. Okay, so that's the point P 0.5 comma 1, and Q is a neighboring point. Use the calculator to find the slope of the secant with x equals 0.1. Okay, so be careful in your calculator and make sure it is in radian mode. That's all I would say. Okay, RAD, the angle is in radian mode, because calculator will have the degree and the radian modes. Other than that, you would be good here. Okay, what you will do, you will calculate sine pi, be careful with parentheses again, times 0.1 minus 0.1 divided by not y 0.1 minus 1, the y1 p, y1 is p, the y coordinate of p. Where was I? Yeah. Okay, and denominator would be y2 minus y1 over x2 minus x1, that will be 0.1 minus 1. Okay, this was not was times there, maybe that's confusing, so let me put parenthesis there. Okay, whatever that number is. A rock is thrown upward on the planet Pluto with velocity that, the height is given by this. It's a different planet, so different gravity, that's all it is. Okay, and average velocity on the interval can be calculated. You know the routine by this time, can skip that. I'm just going to read that question. Okay, estimate the t is 0.06. We need to estimate at that, and it doesn't say how you do it. Okay, see, now we are gradually, now the questions are making you independent. Okay, you have to estimate the um, current flowing at 0.06. Okay, but they don't talk to you about intervals, right? So what you can do is, to recognize the pattern, or first you can try with this interval, 0.04 to 0.06 or 0.06 to 0.08, and the value that you get, if it is already close to one of these without ambiguity, go for it. Okay, I am telling you, for example, if you get negative 375, I would not be so confident, because there is 382.5 and 370. you can't say they're close. Okay, suppose I had taken this interval, then what I would do, I would take the other interval and again compute and see if that is closer to anything. Okay, and if that is not enough, you want to double down and double check, take a larger interval, take zero point 0.2 and zero point 0.6. Now when I say larger, not the thing in between, you take this value and this value. Okay, and similarly that 0.06 and 0.10. And by the time you do all those averages, in case if the values are not getting close to, if you are not confident about to which value it is close, by the time you would be confident, okay, which one of them is the most nearest answer. Okay, point 1 comma 2 lies on the curve. Estimate the slope of the tangent line to the curve here. Again, this is again a similar problem, but now analytic. You're not given any table of values. You do it on your own, so what would you do to estimate? Okay, not exact, to estimate, I will calculate y of the x value is 1 here. Okay, so 1.1 minus y of 1 divided by zero point 0.1. Okay, so that will be 2 divided by 1.1 squared minus 2 over 1 squared divided by zero point 0.1, and then I will get an estimate, and I probably will already be able to figure out where it is close to. Okay, and just to reinforce what we saw earlier, if you want to do it precisely analytically, you do the interval 1 2 is one of the points, and you will go to 1 plus h. Okay, in which case the value will be 2 over 1 plus h squared, right? Because the function is y equals 2 over x squared. With p, it is 2 over 2 1 comma 2 because it's 2 over 1 squared. Okay, that's why it was 2. Now instead of 1, if you go to 1 plus h, a nearby point, the y value will be 2 over 1 plus h squared. Now you take the difference, 2 over 1 plus h squared minus 2 over h, basically 1 plus h minus 1, which is h. Then you simplify that. That requires some algebra work. Okay, and at the end, you once you have simplified and cancelled the h in the denominator, then you plug in 0 for h and you will have your answer. Okay, using the graph below, find the slope of the second line, PQ. Okay, I'm just doing varieties of problems for you here. Now this is about reading the coordinates on the graph. Okay, point Q is 2 comma 12. As long as you are able to read the coordinates of the 2 points, use the formula y2 minus y1 divided by x2 minus x1. Okay, and that will be 12 minus minus 6 will make it plus 6 divided by 2 plus 1. So that would be 18 divided by 3, which is 6. And the answer is 6 here. Okay. All right. The data below shows Usain Bolt. I don't know if you remember or have heard about him, the Jamaican run, right, who broke the record in 2008 Olympics. And what is given here? It's 100-meter sprint. The time and the distance he covered, and what you have to find between 60 and 90 meter marks. Okay, Similar question like before, but with a small difference here. Just want to point that out. You are not given in terms of times here. Now this is interesting. You are asked to find in terms of the dependent variable. Time is the independent variable. Distance covered is the dependent variable here. But that's okay. If when there is a relation, one-to-one relation in a function, and the time would correspond to a precise distance, you can also use the y values to decide on what interval you are talking about. Okay. By the way, in the notation for average velocity, you will not write 60 to 90. Those are y values. You still write 6.32 to 8.7. Okay, unless you flip the whole idea and convert this as distance as the independent variable and time as the dependent variable. Can be done mathematically, doesn't make sense in real world. Okay, if you didn't do that, if your s is a function of t, like if s is equal to s of t, like that, if that is our interpretation, then we should write the interval in terms of x only. Okay, so we are computing the average velocity on that interval. Okay, conceptual clarity. Okay, well, we're towards the end. We're on the last problem. That's great. For the function f, whose graph is shown, estimate or find the limit x approaches -4 of f of x. Limit. Okay, this is a precursor, to what we're going to do next. Just giving you the idea. X is approaching 4, -4. I have to zoom in the graph and maybe override to show you what's going on here. This is a tricky business. There is -9 here. Okay, that's 1, -1, 2, 3, -4 is here, where I have to override. That's a bad choice of color. Let me use black. There is an asymptote here. Remember the concept of asymptote? Okay, there is a vertical asymptote here at -4. Hope I'm saying the correct thing. That's the y-axis. So 1, 2, 3, 4. Yes. At -4, there is an estimate. And the question is, what is the limit of the function? And you see that it's going down, right? But luckily, both of them are going to same negative infinity direction, right? So answer is here. You already, hopefully, you didn't see it already and spoil your thinking. It's negative infinity. Okay. So this is another interesting idea. We will talk later in limits in more detail. You could say limit does not exist. Okay. Also will be fine. But if you have to be more precise, more accurate to the situation, you would say the limit is negative infinity, right? That is more informative than saying limit does not exist. Although, whenever limit is not finite, you are allowed to say limit does not exist. But it's like, answering to somebody, right? We need to be clear to ourselves. So saying negative infinity is better than saying limit does not exist when it is clear. Okay. Sometimes you really can't say whether it's infinity or negative infinity or anything in between. In that case, you say limit does not exist, and that would be fine. Okay. Thank you. Don't forget to do the homework problems on this section. As I said, the document is in the description, but you can also see it here. Okay, these problems from section 2.1. See you in the video for section 2.2. Okay, bye.